In this video, I wanted to do a quick review on fundamental theorem of calculus part 1. And fundamental theorem really establishes the relationship between a derivative and an antiderivative. So what you'll see here is I'm taking the derivative of the integral. And just in general, I want to do this with just a general formula. Okay, I want us to just think through the steps. So let's say we got just f of t dt. The variables are not really important. They just shouldn't be different. The bound should not be the same as the variable in the function. So let's just say we're going to do this by hand. We say I want to know the antiderivative of f, and I'm going to call it big F. Little f is the function. Big F is its antiderivative. So I find the antiderivative, and of course I'm going to leave this derivative statement out front. Okay, and what we always do when we're doing an integral is we find the antiderivative, we did, and then we evaluate. Okay, well, to evaluate, of course, we just plug those bounds in to the antiderivative. That, and we still have to find the derivative. Okay. Well, let's think this through. If we need to find the derivative, big F is a function. If I plug one in, I get a number. So the derivative of this is just 0. Okay. And we've already established that the derivative of big F is little f. So what we get out is the original function, but a function of x instead of t. So coming down here to this problem, when I take the derivative from 1 to x, again, just 1 is really unimportant. Any constant would have yielded the same thing because when it's plugged into a function, it's a number and its derivative is 0. I end up with the original function, but as a function of x instead of t. So the answer is just 3x cubed minus 5x. Now, the next one says 1 to 4x squared. So here's what I want to do. I want to go just modify my work up top. So let's just say it was 4x squared here. So, of course, that would change this bound. And then I would have plugged a 4x squared in. And now, that doesn't change the fact that this derivative is 0. But if I'm going to take the derivative of big F of 4x squared, it would be little f of 4x squared. But then I would also need to use chain rule to multiply by the derivative of the inside, right? You take the derivative of the outside, leave the inside alone, multiply by the derivative of the inside. So what this tells me is that I spit out the original function, but as a function of 4x squared rather than t, and then I multiply by the derivative of that bound. So what that would look like down here is I would have the original function, but 4x squared instead of t, and then at the end I would multiply this entire thing by the derivative of the inside. So let's do another. We've got the derivative of the integral from 1 to cosine. So this is going to be 3, and we're going to have cosine of x cubed minus 5 times cosine x. And then we multiply by the derivative of the inside, which of course, the derivative of that bound, which is negative sign. And this last problem, you'll see it goes from x cubed to 0. Again, what the constant is really isn't important, but I would like it to go from constant to x cubed. And of course, when you change the bounds, you simply change the sign of your answer. So we're going to have negative 3x cubed minus 5x cubed, and then multiplied by the derivative, which would be 3x squared. Sorry, my writing's a little sloppy there. So again, fundamental theorem just establishes this relationship, and that when you take the derivative of an integral, you spit out the original function. But what the original function is a function of is dependent on the bound, right? Here it was a function of x, then 4x squared, then cosine, then x cubed. But then, because of chain rule, we end up multiplying by the derivative of that bound.